people like Giuseppe Mussardo, Paul Wigman, Leonard Susskind. And, Leonard Susskind is the kind of physicist that used to think that when we grow up, we want to be like him, right? So actually, this is my daughter. And here she is studying transience theory. Okay. So, all right, more seriously. Okay. So I think before I start, it's useful to say that the subject of my talk, field theories for fractals, we can say that this is a subject which is in the interface between quantum field theory and condensed matter theory, right? And it represents recent progress in both fields, okay? So I'll try to make this clear along the presentation. And this is a work in collaboration with the grad students, Guilherme and Wesley, and a collaborator from Boston, Claudio Chamon, okay? So please feel free to interrupt me to any point for questions or comments and so on. So here is the outline. By following the advice of the organizers, I have divided the presentation this way. So these two first parts are kind of more introductory ones. So I will review some background material. And in part 3, I will discuss some examples of fractal system, the corresponding effective field theories, and I will present some new results, okay? And session 4 is just a conclusion. All right, so I think a good starting point to the discussion of effective field theories is these two remarkable physical properties, scale dependence and decoupling. Okay, so let's start with scale dependence. Scale dependence, we use, say, an energy scale or a length scale. These are more or less equivalent. And the point is that the physics we observe depends on the scale of observation. At new scale that you consider, new degrees of freedom become relevant for the underlying physics. I will provide a specific example in the next slide. And another important property is decoupling, which means that the infrared physics is essentially insensitive to UV physics. Okay, so these two properties actually enable us to make progress in physics in the sense that we can study one scale at a time. Okay, so let's consider, for example, a fluid. Okay, so and let's characterize the involved scale in terms of a length scale L, and we can see here the hierarchy of scales. For example, if you start here. In the macroscopic scales of this order, we can use a hydrodynamic theory, which means that we can treat the fluid as a continuous medium, a continuous portion of matter. And as we go to shorter and shorter scales, some new degrees of freedom start to become relevant. For example, start from here. New degrees of freedom, like quantum mechanical degrees of freedom, start to contribute to the underlying physics. And in order to describe properly the physics, we have to take them into account. Okay, so we can say that to understand hydrodynamics, we do not need to know string theory because of the coupling of scales. Okay, and now we move into the effective field theories, and the effective field theory is the suitable framework to take advantage of these two properties. The key point is that we can always provide a kind of hydrodynamic description in the sense that we can focus on the low energy physics without consider the high energy sector of the theory. So it's especially useful for describing complex physical systems involving many degrees of freedom, like that one in many body physics, okay, where we are mostly interested in the low energy physics. So this is the kind of strategy we will pursue along this presentation. And typically, the low energy physics is encoded in an effective action or in an effective Hamiltonian. I will use frequently this term effective action. Okay, so the next question is how to construct an effective field theory. Okay, so there is no general recipe. It depends on the UV theory we have in hands, but roughly we can imagine two kinds of situations. Okay, so let's discuss these two kinds of situations. We can have, for example, this first one I will call, it is usually called top-down approach. And in this case, we start with a UV theory, and this UV theory is amenable to computations. This is frequently the case when the UV theory is perturbative or even exactly solvable. Okay, so in this case, we can, in principle, to obtain the low energy effective field theory from the UV1 through a straight line. I will make this more precise in the next slide. This is a procedure more or less systematic and essentially depend on our ability to dissociate high energy and low energy modes. The second option is called bottom-up approach. And the point is that this UV theory is hard to work with, right? So essentially there is no option. We have to construct directly the low energy theory. And in this case, symmetries and dimensional analysis are very helpful here. Okay, I'll describe a little, in a little more detailed way, the top-down approach first. So let's call the microscopic degrees of freedom generically as sigma, and the UV scale as lambda 0. And we are interested in the behavior of the partition function. In this case, the key point is that is a convenient and faithful representation of the microscopic degrees of freedom. And this is related to manageable dissociation of high energy and low energy modes. So in a very systematic way, we can think like this. We start with the microscopic variables, and we represent them in a convenient way. And we can decompose it like this. So as I said, this is very schematically, but the point is we can dissociate the high energy modes from the low energy modes. Okay. In this case, the partition function can be written in this way, and the effective action is formally defined by integrating out the high energy modes. Okay, so this is the formal definition. And the typical form of the effective action is in this way. It is given in terms of an expansion in local operators, right? And the important point here is that this action has some parameters. All the UV information is encoded in these parameters, the coupling constants of the theory, and the operators all dictate the low energy dynamics of the theory. So the object which are interested in this seminar are objects like this, okay? So let's discuss an example. A very famous one is the Ising model. It is defined, consider, for example, here in 2 dimensions, square lattice, and we attach to each side some discrete variables that can assume plus or minus 1. And the Hamiltonian involves the sum of first neighbor, right? The UV scale here is essentially the lattice spacing, L0. And in this case, we can proceed straightly from the UV to the infrared to derive the effective field theory. So the effective field theory is given in terms of a real scalar field with a potential that carries the symmetry breaking pattern, right? And it describes 2 phases, which corresponds the order and disorder phases of the Ising model. So this is a typical example of top-down approach. We can start from the UV and get the infrared theory in more or less a systematic way. All right, now let's discuss the case of the bottom-up approach. So in this case, there is no straight line to the infrared, and the question is how to proceed. So we can use the Feynman's method. What is the Feynman's method? think hard and write down the answers. It's not so easy to do this. And more seriously, we can get clues from experiments, symmetries, dimensional analysis, and intuition, and I think that could be helpful here. And the key point is the proper identification of the couple degrees of freedom. So in general, these are quasi-particle excitations with independent dynamics. So in many cases, the quasi-particles may not resemble the original degrees of freedom. And in this case, we write down the effective action without having in hand the ultraviolet theory. Right, so this is the form, again, this is the form, it is given in terms of local expansion, but now it is not directly connected with the UV theory. I will provide an example of this case. So another very famous one, which will be useful for our proposals, and is the quantum Hall effect. Okay, so the quantum Hall, you'll consider a bunch of electrons moving in a plane in the presence of a perpendicular strong magnetic field. Right, so we have a lot of ingredients acting on the electrons. They try to describe circular orbitals, and they feel a strong Coulomb repulsion, exclusion principle, and we can construct UV theory, UV Hamiltonian, given terms of electron degrees of freedom. And the simplest form of the Hamiltonian that captures the essence of the quantum Hall can be written in this way. So this is essentially the Coulomb potential projected onto the ground state, the lowest Landau level. So these operators, P, L, 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 triple L, are projectors onto the ground state, right? So this is what makes this Hamiltonian a quantum one. In this case, the UV scale is the magnetic length, right, which is dictated by the magnetic field. And the key point is that this Hamiltonian is non-perturbative. So essentially, we cannot proceed analytically, and we have to consider a kind of top-down, a bottom-up approach, and write down directly the effective field theory based on symmetries and dimensional analysis, and so on. And in this case, it is given in terms of a Chern-Simons theory. I will discuss more about Chern-Simons theory, but before that, I think it's useful here to note that these ingredients together produce highly ordered internal patterns, and essentially the system behaves like a quantum fluid with internal order. So this is an example of topological order. Okay, so this is the first part of the seminar, and now I will start to describe a little bit more about the Chern-Simons theory. Is there any question at this point? Okay, good. So I will continue. And now I will discuss a little bit more about the Chern-Simons. So I'm consider the action here in a compact form. And also I have introduced the big A. And the little a is the previous gauge field, which includes the collective behavior of electrons. So this is an example where the proper degrees of freedom, low energy degrees of freedom, are not like the original ones. So all the collective motion of the electrons is codified by this gauge field. And big A is background electromagnetic field. It is used to measure Hall conductivity. This coefficient must be quantized in the sense that it is an integer, so that this theory is invariant under all gauge transformation, including the large ones, even when the system is placed in a non-trivial manifold. I will discuss more about this. We can compute, for example, the Hall conductivity, just integrating out this field, this gauge field here, and the coefficient of the effective action for the external magnetic field is the Hall conductivity. So here we get the quantized Hall conductivity, and if we consider this number k to be an odd, we reproduce the Laughlin series for the fractional quantum Hall effect. Okay, so next I wanted to describe the operator content of this theory. It is given in terms of gauge invariant line operators, because these gauge invariant line operators essentially describe quasi-particle excitations. So this is a typical form of a line operator. And we notice here that this line is along all directions in this system, in both spatial directions, for example. And that's to say that quasi-particles can move throughout the system. So one important point, which is useful in to compare with the Fracton cases a little later, is that the gauge invariance dictates the mobility of excitations, because it dictates the form of line operators. And by studying these line operators, we can determine the properties of quasi-particle excitations by computing this kind of expectation values. And for example, if you choose a closed path, like the union of these two paths, which physically corresponds to the situation when where one particle goes around the another one, we can, for example, determine the statistics of these quasi-particle excitations. If we parameterize the excitations in terms of conservative currents like this, then we can write that expectation value in terms of a current of the current of the action in the action. In other words, I want to say that the effective action, including the quasi-particle excitations, is nothing else the original action in the presence of external current. So this also will be useful in the study of fractal systems a little later. Okay. Another important property of the Chern-Simons theory is that it's sensitive to the topology of the manifold. This means that if we place the system on a non-trivial manifold, like a torus, for example, we get a non-trivial ground state degeneracy. And in general, it's given this way. K is the coefficient of the Chern-Simons, and G is the genus of the manifold. This case of the torus is especially useful because it essentially corresponds to a plane with periodic boundary conditions. If you identify these two sides and these two sides, so this is essentially the torus. And the case of sphere essentially corresponds to an infinite plane, right? Because we can project up to a point, we can project all the whole sphere into this plane. So in an infinite plane, the ground state is unique, but in a non-trivial topological manifold like a torus, the ground state has non-trivial scale like this. Okay, so now I will move to the case of fractal. We are ready to construct this kind of systems. And before discussing some specific model of fractals, I will try to use this kind of layer construction by using the 2+1 dimensional topological order as a kind of a building block. Of course, this is a trivial construction of a highly non-trivial phase of matter. So let's imagine the following situation. We consider layers of quantum Hall effect, for example, forming a stack of layers, right? So forming a 3+1 dimensional system now. L is the linear size. And also we will not introduce interactions so that the electrons cannot jump from one layer to another one. So the electrons can move on along the layers. Okay, so let's see what are the properties of this system. So this is a gapped system because the spectrum is additive. If we compactify each one of these layers in a torus, like I did previously, so we get a topological degeneracy, non-trivial topological degeneracy for each layer. And then the ground state degeneracy of the whole system is the product. So it's going to be in this way, a number to the linear size of the system. So you see that this is strange in the sense that it represents a kind of subextensivity, right? For example, if you take the log of the ground state degeneracy, this is related to the entropy. And in this case, the entropy scales with the linear size and not with the volume, okay? So there's a kind of UV-IR mixing in the sense that if we modify a little bit this system, we make a UV modification by adding one layer here, this will affect a low energy property, okay? It will affect the ground state degeneracy. So this kind of UV infrared mixing. And there's a trivial property, which is the restricted mobility, because we are not assuming that the electrons can change the layer. So if you define, for example, the dipole between two charges in this way, so the perpendicular component of the dipole is conserved. Okay, so we see that the restricted mobility is related to the conservation of high order poles. So all these properties are very unusual properties, which are not present in a typical quantum field theory. They seem to contradict the essence of effective field theories because of the UV-IR mixing, and this is challenging from the field theory perspective. Okay, so the next point is try to understand these properties arising in a non-trivial model. So the first model with fractonic properties was constructed by Chamon in 2005, and this model is a simple one and is defined in the following way. So let's introduce these operators OX, right? So let's call these octahedron operators, and we distribute Pauli matrices along the directions according to this picture, right? So this is formally defined here. And these octahedron operators have some important properties. The first one is this one. If you square the operator, you get the identity. And this means that the eigenvalues are plus or minus 1. And another important property is the fact that all these operators are simultaneously commuting. Okay, so we used to say this as commuting projectors. Okay, and then the Hamiltonian is a sum, simply defined as a sum of all these operators. Okay, so we can find the eigenvalues for all of these operators simultaneously. So this is an exactly solved model. And in principle, we can construct the spectrum. So let's understand the form of the spectrum. Right? So let's start with the ground state. So the ground state corresponds to the situation where all the eigenvalues are plus 1. Okay, and above this ground state, we can construct excitations, and the low-lying excitation corresponds to 4 eigenvalues with value minus 1. Okay, so the question is why, and the point is that the application of a local operator like sigma 1, sigma 2, or sigma 3, sorry, gamma 1, gamma 2, gamma 3, which are Pauli matrices, always create 4 defects which live in a plane, and we can assign a charge for these defects. So it's small here, but I will do this. So there's minus, plus, plus, and minus. And another important point is that this configuration is always in the form of a quadrupole, right? And the key point is that this kind of configurations provide some mobility for the system. So let's understand this. So imagine we consider, for example, this dipole. Let's represent it here, and then we create a quadrupole configuration here, precisely above this one. So in such a way that these two charges and these two charges will annihilate each other, and the global effect is the dipole to jump to this position. So quadrupole configurations imply the mobility of dipole excitations. There is no single charge mobile excitations in this system. So there is no single charge mobile excitations, but we can construct some bound states like dipoles, which are mobile. So this is called usually a type 1 Fracton system, right? And the ground state degeneracy of this system can be computed, and it's also scale with the linear size of the system. So this is the exact result for the ground state degeneracy. Okay, so the next step is try to construct the corresponding effective field theory, right? This is addressed in this paper, and as this is an exactly solvable model, in principle, it's amenable to a top-down approach. It depends on a faithful representation of the microscopic operators. So this is the map which we propose. So this is a kind of bosonization map. And for those who are familiar with the hierarchical construction of quantum Hall effect, can see some similarities here. But let me try to explain some important points here. So in this case, we have two independent Pauli matrices in the sense that the third one can be obtained from the product of gamma 1 and gamma 2. So in principle, we need two different fields in this map. And here we have some parameters. We have some freedom to choose them. But I will not fix them at this point. Okay. A key point of this representation is that we can define some commutational relations between these new fields A, such that this map reproduces properly the algebra of Pauli matrices. So this commutation relation ensures that. Okay, so then we have a map with connected let's operators with operators that possess a well-defined continuum limit. Okay, so this is what we call a faithful representation. Let's try to see if it works. And the first thing is to consider the continuum limit. So we use this representation in the octahedron operators, and as we take the continuum limit, we get something like this. You have that parameter k and the parameters t are encoded inside these big D operators, which are derivative operators, second order derivative operators, depending on special combination of coordinates. So, for example, if you have direction 3 and direction 1, these coordinates are along diagonal. Okay, and then we can immediately write down the effective action. This is Chern-Simons-like effective action, which contains two kind of terms. So the first term is essentially the ground state constraint. We remember that the ground state corresponds to all eigenvalues, like all the eigenvalues equal to 1. So we impose this here in terms of a Lagrange multiplier A0. This will enforces this to be in the ground state. And the first term is responsible for the commutation relation. Okay, so the theory we have obtained is a fully gapped theory, which is also gauge invariant, and the gauge transformations are in this way. Okay, so the time component is more or less usual, but the A1 and A2 components transform according to these non-usual derivative operators here. Okay, so now we can see the consequences of this gauge structure, and we follow the strategy in the previous case of the usual Chern-Simons theory. Okay, so we couple the theory to external currents. In order this coupling to be gauge invariant, the current must satisfy the continuity equation, and the continuity equation is like this. And we see some interesting properties here. So the first one we have, of course, the conservation of charge in the whole system. If you integrate it in the whole volume, you get the conservation of the total charge, right? But because of this form of derivative operators, if you integrate, for example, in a spatial slice like Tx13 plus, T23 plus, these two terms will be surface terms, and we still have conservation of charge, even this subdimensional manifold. Okay, so this is related to the layer structure that I discussed in the previous slide. Okay, all right. And the next step is to use the gauge structure to study the type of gauge invariant line operators, right? So I think it's useful to start with a simple dimensional analysis, and this is a non-relativistic theory. So the typical dimensions of spatial coordinates and time are different, and we remember that the line operators are dictated by gauge invariance, right? So now we can construct the line operators. So the first one is a line operator.
Sorry, Pedro. I think we have a question. I think Andrea is with the hand.
All right. Sorry, I'm not seeing the audience. So.
Yeah. Andrea?
Yes.
Please.
Yes, I'm a bit confused because you said the system is 3 plus 1 dimensional, but then the effective action is 2 plus 1 dimensional.
No, the effective action is 3 plus 1 dimensions. The point is this.
So it's not Chern-Simons.
It's not Chern-Simons. It's Chern-Simons like, yeah. Let's go back a little bit. Thank you for the question. We see that essentially these index structure here are not space-time indices, right? So B goes from 1 to, we need 2 independent fields here, right? So we have 3 fields, A0, A1, and A2, but these 2 indices are not related to space-time. Is that clear?
Yeah, but the coupling to the current index are related to space-time.
Yeah, I relate, but this we can think in a kind of generalized form of the current, in the sense that we couple to the fields by requiring only gauge invariance. So the currents are also different. And but in the paper we have studied some explicit solutions of the continuum equation to explore the physical meaning of this current. And the solution, the typical solutions of these continuity equations are the quadrupole configurations.
But if you tell me that the J1 and J2 are not space-time components, this is not a continuity equation.
Yeah, it's a kind of generalized version of continuum equation.
Okay.
Okay, it's just a requirement for gauge invariance. I just using.
I understand. Yes, this I understand. But geometry of this is not. Okay, please go on.
Okay, thank you. All right, so let's try to construct the gauge invariant line operators, and the first one is along time direction, and this is required by the gauge invariance of the system, right? And we see some two important properties here. The first one is that this represents the trajectory, the word line of a particle only along the time direction. So it's a completely mobile particle. We used to call this a fracton. It's a monopole. And the another property is that this is not a dimensionless combination. This is not a dimensionless combination because of these dimensions here, so that we need to introduce a dimensional parameter here in order to produce a properly dimensionless argument of the line operator. And this dimensional parameter here is nothing else, the lattice space. So this is a manifestation of UV infrared mixing. All right, so this is the first type of line operators. The second type of line operators are these ones. So let's study, for example, this first, one example. So this structure is gauge invariant. Let's consider, for example, one of the signs plus, right? So this combination is gauge invariant, and you see that this line is along diagonal. So this can be associated with the motion of the dipoles. And to make this more precise, we integrate out in the perpendicular direction, which corresponds to the size of dipole. And still you have to introduce the lattice space in order to produce properly dimensionless line operator. And we can proceed in the same way with the other directions. So all these spatial line operators represent the motion of dipoles along lines. So these particles are usually called lineons or linos, right? And with this theory, we can also compute the ground state degeneracy. Of course, we need to regularize it, which is essentially kind of a discretization. And this is also another way to see the UV-IR mixing. Okay, what about the time, Thiago?
You have more, 10 minutes? 15 minutes?
Perfect. 10 minutes, I think, is fine. So this is the last model I want to discuss. It's the called Ha model. So it's a still more exotic fracton phase. I will discuss this. And the model is defined in terms of these cube operators, right? So the first difference compared to the previous case is that now the local Hilbert space is higher dimensional. Essentially it's 4-dimensional because we have a tensor product of Pauli matrices here. We represent in terms of Dirac matrices. And the Hamiltonian is simply given in terms of a sum of these cube operators. We have two types of cube operators, right? As in the Shamon case, the square of these operators reduced to the identity, and they all are simultaneously commuting. And again, this is an exactly solved gapped model, right? So it's interesting to consider the spectrum, and there are some remarkable properties here. The application of a local operator at a point of the lattice again create 4 excitations, but now in a little bit asymmetrical way, forming this tetrahedral structure. Okay, so they form a tetrahedral. And here are the cubes which are with the corresponding eigenvalues -1. So we have these 4 excitations. And because of this form of excitations, as a result, all the excitations are completely immobile. We cannot use the same mechanism we used before to construct bound states which are mobile. So this is called a type 2 fractal. And if you try to move apart these excitations, you create a lot of charges inside this, and these charges are organized in a fractal structure. Okay, so this is quite peculiar. We have a model where all the excitations are completely immobile. Okay, so the puzzling here is what is the effective field theory. This is addressed in this paper. It was recently posted on arXiv. And this model has some similarities with the Shamon model in the sense that the Hamiltonian is given in terms of sum of commuting projectors. This is also an exactly solvable model. And of course, it's not at all trying to use the same strategy, okay? So we'll follow a top-down approach and try to derive the effective theory in terms of gapped gauge theory again, right? This is a little bit puzzling because we have seen that a gauge structure in general gives rise to gauge invariant line operators, and gauge invariant line operators describe the motion of quasi-particle excitations. So the question is how to construct a gauge theory without line operators, because I have discussed it. All the excitations of the Hakode are completely modeled. So let's try to understand this. And again, I will use the same representation as before, but here we see the first difference. The first difference is that as the local Hilbert space is higher dimensional, we need more fields here, right? We need 4 fields in this case. So we remember that the model is 3 + 1 dimensional, but in this case we have these 4 fields, and we follow the same procedure, right? We express the cube operators using this map, and we take the continuum limit, right? And the result is a little bit strange because the presence of this term here, this is the 0 order term in the continuum expansion, continuum limit expansion. And you see that there is no derivative operators here, and consequently, it is not gauge invariant. The first order terms vanish, and we have here the second order terms, right? These derivative operators, D1 and D2, are defined in this way. And I will try to understand the physical meaning of this term. I marked here in red because this has an important, one important point is that this structure here is precisely this structure together with this D1 operator. Okay, so let's try to understand what's going on here. So I just repeat the figures here for convenience. And let's consider the continuum limit. So the 0 order term essentially corresponds to the collapse of the cube operators to a point. So imagine you put your frame in the center of the cube. And if you multiply all these matrices, both cube operators reduce to the identity, right? So this, the map is not reproducing an important property of the lattice. So we could try to demand that this combination vanishes, but this is too strong to produce a consistent field theory, all right? So we can do this in a weaker form in terms of matrix elements. So instead of impose this at the operator level, we impose this condition in terms of matrix elements. So this is more or less like BR-state quantization of gauge theories and can be thought as a condition for selecting physical states, right? So we will deform the theory describing a larger Hilbert space, but after this we need to project the theory inside the physical Hilbert space according to this condition, by using this condition, right? So in proceeding this way, we get the cube operators, only the gauge invariant part. And here again, I have introduced this big D, which is essentially, it's just a combination of the 2 derivative operators. So in this case, we end up with a gauge theory, okay? And again, we can construct the effective action. You see the ground state constraint here. Alpha is 1 or 2 because we have 2 flavors of cubes, 2 types of cubes. And here are the Lagrange multipliers. And this first term is responsible, again, for the commutation relations between A's fields, right? This theory is invariant under gauge transformations like this, right? And without the condition for selecting physical states is just a type 1 fraction theory, right? So in this case, without that projection, it contains line operators that represent mobile excitations, okay? So again, we can couple 2 external currents and the requirement to be gauge invariant leads to a kind of continuity equation like this. And one interesting property of this continuity equation is that it leads to infinitely many conservative charts, which are parameterized in terms of a function f, which is annihilated by the big D operators, right? We remember that big D operators are given in terms of D1 and D2. So this gives restrictions on the mobility of excitations, but still have mobile excitations. We can construct line operators. We describe mobile excitations in this case, right? So let's try to understand how to project onto the physical subspace. Okay, so I just repeated the condition here, and we consider dynamical information. It's kind of flux attachment. This comes from the equation of motion of the A0 in the presence of currents, right? And this relation leads to the following conservation law, and we project this conservation law inside the physical subspace in this way. So let's see the right-hand side of this expression, right? And in the first line, we see that in order this produces the correct conservation law, we need both D1 and D2 annihilating the function f. So we can integrate it by parts, and this will vanish. But as we are projecting inside the physical subspace, we identify here these terms in red are precisely the condition for selecting physical states. And the key point is that after the projection, inside the physical state, the function f is a little more general, because we only need that this condition, f must be annihilated only by D2, not by D1 and D2 like in the previous case, right? So the point is that this leads to more conservation laws. We have a more general class of solutions here. We have studied this in detail in the paper. And this leads to more restrictions on the mobility of excitations, leading to the complete immobility of all excitations. Okay, so it means that inside the physical subspace, all the excitations are completely immobile, right? So in this sense, the type 2 fracton character is embedded into a type 1 theory, okay? All right, so this is the way we describe the physics of the high code, right? And just to conclude, I would like to point that the field of fractons is in the initial stage. More generally, the exotic phase of matter opened the doors for a new surprising worlds, connecting distinct fields and with many open questions. And my feeling concerning their studies like this. So this is my propaganda for the field. This is the Ernest Shackleton advertising for crew for the journey to the South Pole. So men wanted to hazardous journey, small wages, bitter cold, long months of complex darkness, constant danger, safe return doubtful, honor and recognition in the case of success. So that encourages me, and I hope it does the same with you. All right, so thank you.
Thank you, Pedro. Thank you very much for the very nice seminar. So before the questions, if you can please turn on the camera, then we can take a picture of everybody. And if you have any questions, please go on. And I have one. I missed it. How do you define this type 1 and type 2 fractons? What's precisely the definitions?
Okay, so type 1 fracton, it contains mobile particles, any kind of mobile excitations. We use to say fracton 1, and type 2, there is no any kind of mobile excitations, right?
Hi, can I make a question?
Yeah, sure.
Thank you, Pedro, for this nice talk. I was confused about the reason of the fractal spectrum and the relation of it with the mobility of the excitation.
Okay, so
there is some connection between the immobility of the excitation and the fractalization of the spectrum.
yes, yes. Let me share screen. I think it's easier to show some picture. Can you see, right?
Yeah.
We remember that, let's go back a little bit in the case of Shamon, just to contrast. Let's consider this case. So in this case, we have a very symmetric form of excitation. So you can use this, this configuration to produce mobility. In what way? In this way. So you just produce, let's draw a picture here. You just produce another configuration like this, and precise at this position. So these two charges will have annihilated to each other, and the global effect is the dipole to jump from here to here.
Right.
So because of this quadrupole configuration, we can find mobility of dipole excitations.
And
so
in this case, you will find a continuous spectrum, right?
No continuous spectrum, because in what sense you are saying? Because the spectrum, for example, you have a gapped spectrum.
Oh, right.
You have a gapped spectrum between the ground state, the first excited state, which corresponds to 4 minus 1 eigenvalues here.
As I said in the meaning that it is not fractal.
It's not fractal. Yeah, I agree. Mm-hmm. But in that case of the hard code, you see that this form, which is a tetrahedral, you cannot produce another kind of pictures like this, leading to mobility. When you try to put apart these charts, what happens is that the many charts are created inside here. Right, and these charts form this fractal structure. They are organized in a fractal structure. So I think the best way is try to construct this kind, to apply this kind of operator. It's hard to draw here, something like this, and you see that you cannot, you don't have available the same mechanism as before, as in the case of Shamon code. It's more or less a mathematical way to see this.
Thank you for your answer.
Continue this question, because this to me is not clear. So if before you could add the dipolars and make them move, if this is just generalizing dimensions, I would expect that you should be able to add quadrupoles in the same way as you have added dipoles, and that they would neutralize and you could move quadrupoles. Do you understand what I mean?
I think I understand. Let's see this. And the point is that dipoles are not in the spectrum. You see, the first, the ground state corresponds to poles equal to +1, and the first low line excitation contains 4 defects. I'm saying that if you have this configuration in the first excited state, this bound state can move. For example, there is no energetic cost to produce these. So you can stretch the quadrupole configuration. But the dipole is not in the spectrum. I don't know, is it good?
And the quadrupole is in the spectrum in the other one. In the other model, in the HAR model.
It's also in the spectrum, but not quadrupole, because here we have 4 excitations, but actually this configuration forms a tetrahedral.
A tetrahedral. Okay, then there is no way you can.
Yeah. That's the key point.
I see. Okay. Thank you.
All right. Thanks.
So I think Andrea have a question. Please go on.
Yes, can you explain me again the degeneracy of the ground state? I mean, because you said there is a gap, the system is gapped, but
Mhm.
so you have a degeneracy which grows with the size of the system, but there are no excitation from going from one ground state to the other. That would be massless, right? Is that correct?
I don't think so. But the point is that the ground state degeneracy of the hard code is unknown. All right. I think there is only some bounds for this, the value of the ground state degeneracy for the hard code, but it's hard to define. It's hard to.
No, let's discuss the previous model, which is simpler.
Yeah. The previous models, I think, is we can understand the ground state degeneracy in the following way. And the key point is we have computed this ground state degeneracy in the following way in the paper. We have identified the layer structure. So it's not a layer structure like in this trivial case, because this is organized in a trivial way. But the layer structure of this model, let's consider here. I will try to represent here a three-dimensional, and the layer structure are spatial slices in something like this. Some slices are not perpendicular to this to the original frame, right? But you can proceed with the ground state degeneracy in the following way. Once you have identified the layer structure, we can discretize the system. I will do this now, represent this in this way. So imagine you identify the layer structure. This direction, let's call this W. So is essentially this direction. And you can compute the ground state degeneracy for each layer. And then the final result is the product of all of them. That's the way we have computed the ground state degeneracy. So it involves to put the system in a lattice, right? You have to discretize one of the directions. Otherwise, the ground state degeneracy is infinite.
Yeah, but I mean, but to say the system is gapful.
Is gap, yeah.
So there is no excitation which goes from one ground state to the other. Otherwise, that would be massless, and then you would say I have a gapless state. For example, let's take a lowest Landau level. You put an electron on it, just one. This is a system which has a degeneracy of the ground state, okay, which grows with the size of the system. But there is an excitation from if there is a mass excitation from one ground state to the other. Just move the electron from one orbit to another. Okay, so this system is not gapful; it's gapless. So if you have many ground states, but there is no excitation connecting them, then this is not field theory. I mean, it's like having a spontaneous symmetry breaking, like having not just two states which do not talk to each other, but a growing a number of states that do not talk to each other, growing with the size of a system. So how do you define the field theory? Just you should take one and disregard the other. So if there is no way to connect the two states, two ground states, then they're orthogonal. It's like symmetry breaking, spontaneous symmetry breaking. Am I wrong?
I think it is better. The precise analogy here is with usual Chern-Simons theory. So in the case of usual Chern-Simons theory, the situation is similar. We have, let's put it this way, and let's put it on our torus. right? And in this case, we also have a fully gapped spectrum, which is degenerate. And the degeneracy is gives essentially by this coefficient in the case of torus. So it's the same, it's precisely the same thing. When we introduce this, we identify the layer structure. Each one of these layers works precisely like a Chern sinus. How do you think about the ground state degeneracy of Chern sinus theory?
There are different sectors because they are associated to kind of soliton solutions, different soliton solutions. But the difference here, the number is finite, is independent of the continuum limit.
In the case of the Chern sinus, you mean?
On the torus, yes.
Yes.
K is finite.
Yes, but this is precisely the case of the layers. In each layer, the degeneracy is not dependent on the size. It's just a number. What introduces the dependence on the size is this product. So, for example, we get a number here, depending on the size of the torus. Here we get the same number, and the ground state degeneracy will be the product of this number along this discretized direction.
Okay, so
yeah, that's why I see that each layer is precisely like a Chern sinus theory.
Okay, the conclusion is that I don't understand it, but it's my fault because I know nothing about the subject. Right. Okay, don't worry. Okay.
Okay, so Rodrigo has a question. Please, Rodrigo, go on. Rodrigo? Okay.
Hi, Pedro. Thank you for the nice talk. I was wondering, is it possible to use the effective field theory to study phase transitions out of this fracton phase? I imagine if you start adding perturbations and cranking up coupling constants, eventually you close some gap or something.
I'm not sure if I got your question. You mean, I think we can always think in terms of a kind of bottom-up construction of effective field theories, even when we don't know the UV, how to proceed from the UV. So this is related to your question?
No, I imagine that, say, even on the lattice, you have to use very specific interactions to get the phase with fractal order. If you start adding simpler two-body interactions, you probably drive the system into some other kind of phase. You have to go for a magnetic phase or some magnetically ordered phase. So I was just wondering, in the field theory, if you thought about how this could come about, and if you could use the field theory to study universality classes of phase transitions that have some kind of fracton phase on one side.
Fracton phase on what?
One side of the transition.
I think I understand your question. For example, you mean phase transition between, suppose you have one phase which is kind of ordinary phase, and another phase is a kind of a phase with fracton properties?
Yes.
My simple question is, I don't know. I think it's a very interesting situation, but actually I don't know much to say about this case. Right? Certainly, it's quite interesting, and I don't remember to see discussions like this in the papers I have.
May I comment something? In the context of the fractional quantum Hall effect, so if you move around the Laughlin states, you will get phase transitions into solid phases, which are electron solids, And so you move from single particle localization around the quantum Hall plateaus, and then you get formation of charge density waves if you want, Wigner crystal, and then bubbles, Wigner crystals of bubbles. So if you have a theory to describe the fractional quantum Hall effect, at a certain point you should be able to see the transition to a Wigner crystallization. That could be precisely the kind of thing I imagine that Rodrigo is asking. Is it so, Rodrigo?
Yes, yes. I was wondering how it generalizes to Fracton phases.
And how can you see this in terms of a Chern-Simons description of quantum Hall?
Well, we looked at we have a description of this kind of problem because these phases had been seen experimentally by the group of Jim Eisenstein in Caltech in 2002, I think. And we have some papers in 2004, but we are not looking at it in terms of effective field theories. Although we afterwards looked, we have a PRL 2004, I think, looking at it in the framework of the Hamiltonian theory of Murthy and Shankar, which is some kind of effective Hamiltonian theory for the fractional quantum Hall. That would be also a question I would have, how your type of effective field theory relates to his, because they are also enlarging the Hilbert space and afterwards projecting into the physical subspace, and they can do it as long as they have a system that's gapped. And it's kind of similar. It's a generalization of the Chern-Simons theories, including also dipoles. So maybe there are some similarities there.
What is the reference?
So the one who developed the field theory was Murthy and Shankar. There is a review of modern physics by the two of them. I think it's around 2000. And then we have a PRL. It's Mark Gerbeck, Pascal Lederer, and myself, Cristiane Moraes Smith, 2004, using the theory to look for predictions of possible phase transitions between fractional quantum Hall and other phases of bubbles. And there are a few other ones also by looking at these phases around the integer quantum Hall effect.
Yeah, it seems to be quite interesting. And I don't know this works, but certainly I will.
Okay, if you want to discuss, just contact me afterwards.
Okay.
Yeah.
Sure. I'll do it. Thank you.
Thank you.
Okay. I think Dimitri.
Yeah.
Yeah, I also have a question. So thank you, Pedro, for interesting talk. My question is more in the spirit of Andreas before. So I would also answer his question in the same way you did. I would say that, okay, this is kind of Chern-Simons-like theory. So, and Chern-Simons theory is gapped. So if there's any degeneracy in this gap theory, so it's the same kind of degeneracy. So I would ask then, but is this theory in some sense like Chern-Simons? Is it topological? Because if it, for example, does not depend on the metric, if it has a trivial Hamiltonian, then that would mean that there is no local physical degrees of freedom in this theory.
Yeah, it's not completely topological because to describe fractons, the theory cannot be completely topological. It should depend on some details of the manifold, like this dependence on the geometry. So the lattice space in the presence of the lattice space is a kind of dependence on the geometry. On the other hand, it's a fully gapped theory. So this is like in the case of the Chern-Simons. And but the point is that it's not completely topological.
So, but I mean, does it enter your Lagrangian, for example? I mean, you said that the lattice spacing is somehow appears here, but I think Lagrangian, is it really dependent on the lattice spacing?
I think so, because here.
I mean, we can just look at the formula, and I think there's.
Yeah, we have no space-time indices here, right? So it's hard to define, for example, diffeomorphism transformations. So it's more or less like the same, but for example, you see here we have fields A1, A2, N3, and A4, and the number of fields is related to the size of local Hilbert space, how many degrees of freedom you put to each side of the lattice. Right, so in this sense, I think this is not a topological theory, a completely topological theory. It has some properties. Like I said, if you define this like a sum on some, we discretize one of the directions and we transform it something like this. And you identify the layer structure here. Let's call all these things in terms of layers. So we can identify in each layer a kind of topological Chern-Simons theory, that layer structure, which is in a diagonal direction here, right? But I don't know what to say about the diffeomorphism and topological invariance of this action, right? I think the best thing to say is that to describe a fractal, we need some information of the lattice, some information about the geometry, not on topological aspects.
Okay, thank you.
Sorry, if there are no space-time, if there are no space indices, this is like Chern-Simons theory in 0+1 dimension that is called Chern-Simons quantum mechanics. That is exactly the Hilbert space of these solitonic modes on the torus. So it's like having a product of Chern-Simons theory on two-dimensional torus, but then this is reproduced many times in the orthogonal direction. You see?
I'm not sure about this because I'm saying just that these indices here, A and B, are not space-time indices, but of course the
Okay,
field,
so it's a scalar, right? So
is kind of one, yeah. But the fields of depend on the space and time. So this is a theory in 3+1 dimensions. Are not ordinarily
okay, okay. Well, okay. In this case, I think I'm right, but I have to show this. Okay. 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 Thank you very much.
All right, no problem.
Okay, so I think there is no more questions. So thank you, Pedro, again. Thank you, everybody, for the participation, and see you next week. Okay.
All right, thank you.
Thank you.
Thank you very
Thanks a lot,
much.
everyone.
Pedro.
Bye-bye. Bye-bye.
Bye-bye.
Bye-bye.
Bye.
Take care,
Bye-bye.
guys. Good afternoon.
Bye-bye. Thank you.
Bye.
Pedro, if you send me an email, I can send you all the references,
Yeah,
okay?
sure. I'll do it. I'll do. Thank you very much for calling attention to